Hello everyone, my name is Kalandri Bankoli and I'm a developer advocate with IBM's emerging technology team. So today I'll be walking through our serverless home automation journey. The purpose of this journey is to show how Watson language services can be arranged to create a basic home automation hub from a Raspberry Pi, microphone, and an RF transmitter receiver pair. This will allow for users to turn devices around their home off and on using their voice or cell phone. So first, I'll begin by going through the system architecture. So starting from step 1, the system receives user input either through a microphone directly connected to the Raspberry Pi or through an SMS message sent to a registered Twilio phone number. So to ensure that the Raspberry Pi only records audio from the microphone as needed, we've leveraged a customizable hot word using a service called Snowboy. So a hot word is essentially a way to activate this speech-to-text service, similar to saying Alexa for the Amazon Echo or Hey Google for Google Home. This can be configured by signing up on Snowboy's website, speaking the hot word 3 times when prompted, and then downloading the generated model. So in this case, I've made the hot word Hello Watson. In step 2, an incoming message is received and the payload begins to be processed by a sequence of open-list serverless actions. The reason we're using serverless logic here is that it enables us to offload a lot of DevOps responsibilities, so we won't have to manage updates and dependencies, and because the backend code will only be called on demand instead of hogging resources 24/7. Next, we'll see that step 3 marks the initial open-list action, which checks the message payload type. So if it's audio, the payload is processed by the Watson speech-to-text service. If it's text, it's simply forwarded to the next open-list action in step 4. Moving on to step 5, we'll see the second open-list action, which uploads the forwarded text to the Watson conversation service. So if we look at the action code, we'll see that it's simply creating a JavaScript promise and returning the result once the promise has been resolved. This conversation service analyzes the input text and returns an intent and entity pair. The intent essentially determines which action should be taken based on the incoming command, and the entity determines which object the intent will take action against. So if we show our conversation settings, we have 2 intents configured here, turn on and turn off. We also have 4 entities, which are fan, light, clock, and all. So these can be modified to recognize custom speech patterns by adding synonyms, which can be seen here. The conversation UI also has a sidebar that can be used for testing as well. So if we say turn on the light, the turn on intent and light entity will be returned. If we say cut power to all devices, we'll see that the turn off intent and the all entity will be returned. Steps 6 and 7 mark the final open-list action, which simply publishes the intent entity pair to the Watson IoT platform. This platform accepts messages using the MQTT protocol. In step 8, the Raspberry Pi, which is subscribed to the IoT platform, receives each incoming intent entity pair. And in our final step, the Raspberry Pi emits the corresponding RF signal through the connected transmitter. Alright, so now I'll show the Raspberry Pi and the RF circuit. So I promise it's not as complex as it looks. So a brief run through of each of the components. So of course, we have our Raspberry Pi, which is preloaded with the Raspbian operating system. And we also have a solderless breadboard, which is useful for prototyping circuits without having to use soldering equipment. So to connect the Raspberry Pi's GPIO pins to the breadboard, I've set up this GPIO breakout board and GPIO ribbon. So if you're setting this up at home, be sure that the ribbon's white line is on the side furthest from the USB and Ethernet ports. We also have our transmitter and our receiver pair. So the transmitter has 3 pins and the receiver has 4, one of which is not used. So both require 3 connections to the breakout board. One is for power, the other is for ground, and the third is for data pin, which is connected to the GPIO pin number 17 for the transmitter and number 27 for the receiver. And finally, we have our RF sockets, which can listen on the 433 MHz protocol. To capture the signals that correspond to our sockets, we can execute a program called RF Sniffer, which will listen for any incoming signals on the 433 megahertz protocol. So now you'll see that as I press the on and off buttons on the remote, the corresponding signals are written to standard output. Once our signals have been captured, we can then place the MQTT credentials and RF signals in an environment file that will be loaded by our Node.js server. So if I show the output of the server code here, we'll see it's simply establishing a MQTT client to connect and subscribe to the Watson IoT messaging channels. Once connected, the MQTT client will wait for entity intent pairs and use the code send binary to emit the corresponding RF signals for each pair. Alright, so now I'll show a brief demo where I'll use the system to turn a desk lamp on and off. Hello Watson, turn on the light. Hello Watson, turn off the light. All right, so that concludes our demo. We have a few next steps established for the near future, such as adding a microphone array to improve voice recognition and adding additional sensor types to control different devices like smart TVs and garage door openers. So if you're interested in recreating this setup, please follow the link to our Journey page, our GitHub repository in the video description below. You should be able to find all the information you'll need there. I'd like to thank you for viewing, and please don't hesitate to leave any feedback, whether that be through comments, GitHub issues, pull requests, emails, etc. It'll all be greatly appreciated. Thanks again.